Hello, everyone. My name is Maryleen Ndubuaku, and I'm a lecturer at the University of Derby, where I'm also doing my PhD. So my work is actually at the intersection of machine learning and Internet of Things. So basically, I'm looking at data stream processing, using intelligent techniques on IoT distributed systems. And my talk today is going to be around my research, and I'm also going to be talking about some real world applications in this area and some business use cases. So the topic is edge enhanced smart analytics in IoT-based distributed systems. So when you look at these applications, these applications have been with us for a while, but today actually there are things that are coming in place, and we know that the decision making, like we're looking at faster decision making, we're looking at making quicker decisions with what we do with data. So the difference we see today is when we want a data-driven approach to actually make decisions. So it could be adding more sensors to the system, to collect more data for data-driven decision, or it could actually be using the data we already have to make faster or quicker decisions, or to get more insights into what's happening in the system. So we can see here, like in healthcare, the self-driving cars, gaming, and surveillance, that we want to reduce as much as possible the latency, the delay in making decision, because that delay, just 1 second of delay, can cost someone's life. It can lead to loss of life or damage. And in the case of gaming, those of us that are game lovers, you know that if there is a lag in the system, it's going to affect the user experience and it wouldn't be enjoyable. And in the case of surveillance, we are looking at detecting, let's say, anomalies in the scene. So we want to go from looking at just redundant data to extracting useful insights. And now we're going to be seeing how today's technology is coming in place to improve this sort of applications, improve the efficiency and the performance of the system. So Internet of Things deployment has actually gone from about 5 billion devices as of 2016 to 40 billion devices, and even more devices are being added to the network. And we know that the data that's coming from Internet of Things sensors, it arrives quickly. For example, let's take the greenhouse, autonomous greenhouse, for example. We can have sensors that are deployed to collect data every second. And that data has to be sent somewhere to be analyzed. And that data is also arriving continuously. And we also know that the IoT devices they have low computational power. We know as well, like I've shown in the previous slide, that today we're looking at time critical applications that you want to either you're improving the user experience in real time, or you're actually making real-time decisions that can be a matter of life and death. So the nature of IoT-based systems, we'll look at it broadly in the aspect of the challenges and as well the requirements. So for the challenges, we know that IoT devices, they are resource constrained. Sometimes they are being deployed in harsh environment, for example, in disaster areas where they need to collect data. So some of them may be unmanned. Then we know that they are heterogeneous in nature. So we're collecting data from different data sources, different locations. It could even be, in the case of healthcare, you just have like one patient data being in having different data types. Let's say you have image, you have numerical data, you have time series data, and all of them are all related to the same patient. So how can we handle this heterogeneity? These are some of the questions that come into play when we talk of IoT-based systems. Then we also look at connectivity issues. So for example, in the disaster zone, when you deploy your IoT sensors or in an unmanned area, you may actually have connectivity issues between the data source and the data center. Okay, so those are some challenges. Then for requirements, like we saw, where these days most businesses they're looking to build low latency applications. For example, if you go on a website and it's taking even as little as 10 seconds to load the website, you're already impatient. So it's a fast-paced world, and we're looking at arriving at very low latency decisions. Also scalability. So like we said, the IoT devices, they are increasing in number. They're being added every day. And because they are low cost, low power devices, it's easier to just add more devices. But what that means is that, we are going to have like more data to handle. So we should be able to scale up our system. So as we're adding these devices, we want to achieve, about the same performance in the system. So those are some requirements. Now we look at the cloud computing is the traditional, style, the traditional paradigm for data stream processing. So in this paradigm, we have sensors that are collecting data. So these sensors are the data source. They're sending data to the central location, which is the cloud. The cloud is a powerful entity. It's got, storage, massive storage, and computing capacity. So it can handle all that data. But the problem is that, for example, if you're in an area where, between the data source and the cloud, you're experiencing end-to-end latency, what that means is that it's going to take more time to make decisions. And if you need to make an actuation decision, let's say open the vent, for example, in the case of self-driving cars, you need to stop the car, halt the car to prevent an accident and stuff like that. So it's going to, using this architecture, it's going to really be challenging. And again, we have raw data. All of these sensors are sending raw data to the cloud. So you're going to have like a massive stream coming in, and that can cause congestion in your network, and it can cause network traffic as well. So these are some challenges and a lot more with the cloud. And we're going to see how we can, actually reduce some of those challenges or solve them using edge computing. So in the edge computing paradigm, we actually have the edge device as an intermediary layer. So you can have like several edge devices as intermediary layers. Sometimes you hear cloudlet, mobile cloud, and all other terminologies. But the whole idea is that you have this intermediary layer between the sensor and the cloud. And the edge is not as powerful as the cloud, but mostly more powerful than the sensors, than the data source devices. So what it does is that it can pre-process the data before it gets sent to the cloud. So it's making low-level decisions, or you can say, doing some low-level processing, while the cloud is actually doing higher-level processing. So in that way, we can say that the edge is serving as a backbone to the cloud. It's offloading. The cloud can offload some of its processing tasks on the edge to be handled. And this way as well, if we want to make decisions quickly, rather than sending the data all the way to the cloud, we can actually localize the decision, and we can do some actuation at that edge level. Yeah, so again, when it comes to sending data, we're not sending all that raw data. We can pre-process the data, and we're sending data that is more meaningful and insightful to the cloud. Now, the whole idea of edge enhanced smart analytics is that, we can actually leverage this ability that the edge has as an intermediary layer by performing some pre-processing, and that pre-processing can be done in a smart way using machine learning. So even the edge and the cloud can actually collaborate. So it's sort of a cooperative data processing as a whole, a single distributed system. So we can have machine learning on the edge, machine learning on the cloud, and the data processing can go back and forth between them. And in terms of meeting IoT system requirements, we're going to be looking at how edge enhancement analytics can actually come in handy to achieve the goal of IoT systems or their requirement. So we're going to look at that in two separate parts. So we can use learning technique, which is basically how the intelligent model is being trained. We can also use data reduction technique, so the way the data is being processed. I'm just going to pause and check how this is going. Okay, so yeah, okay. So moving on. Okay. So now we look at the different learning techniques. So we have federated learning, which is basically we have local models, like on the edge. So those models are on the edge, and then they can process the data locally, and the model gets sent to the cloud and aggregated on the cloud. So the advantage of doing this, why do we need it? One is privacy. For example, if a business is concerned about sending its data to the cloud, to avoid the data being compromised, or it wants to ensure privacy of the data. So the data can be trained locally, and then they send the model and aggregate it in case maybe they need to make some global decision with other business units, but don't want to expose their data. So privacy is one motivation. Another motivation is in the case of resource constraint. So rather than having to send all the data to the cloud, the edge node can still, make decision, or can still be trained with, or it can still receive the global model during the model distribution. So so the motivations are privacy, resource constraint, and there are some other motivations as well for federated learning. Then we look at data reduction techniques. One is the dimension reduction, anomaly detection, and clustering. So the whole idea is that we want to pre-process the data on the edge before it's sent to the cloud. So these are different techniques that we can use to achieve that. So dimension reduction is we're still sending the same data to the cloud, but then it is in a miniaturized version. So the data is compressed. So it means that the channel between the edge and the cloud can actually be, freed up, and we can save bandwidth. Then in the case of anomaly detection, we actually just want to send the special data, or the interesting data, as we may call it, to the cloud. And in case of anomaly detection, and a typical example is in video surveillance. So basically, let's say you have a human monitor who ordinarily would be looking at each stream as they come in, but with the edge enhanced model, you actually have an intermediary layer that acts as a sieve, that sieves out the abnormal data and then send the abnormal data to the cloud. So you can even set up an alert system so that, whenever there is anomaly, everyone can be alerted, and it can improve decision making. And by doing that, you tend to miss less of the anomalies, which are in themselves rare. Then in clustering as well. So clustering, when data tend to be similar, you can have a lot of redundancy. So what you can do is to group the similar data, and then you're sending an instance of that data to the cloud rather than the entire data. So this is a way to reduce redundancy in your data transmission. For example, in the case of data summarization, so you have these raw data, input data, you try to find some structure and some similarity to the data. And when you've put the data in clusters, you can just choose like a sample of that data and send across your network just to summarize what is going on. So a typical example is in scene understanding. You want to really know what's happening in the scene without having to look at every second or every second of data coming in. So you can actually use this approach. So what are some of the benefits of edge enhanced smart analytics? So one, like we said, we incur lower transmission costs because we're actually leveraging the edge to pre-process the data. So we can, reduce the cost of data transmission, the data we're transmitting, is not only fewer or compressed, it's actually more meaningful and more insightful as it goes to the cloud. And by doing that, the cloud can then, let's say, perform some higher level tasks, maybe objects recognition or correlation of anomalies, or perform some global task. So it frees up the cloud for higher level decision. Then faster actuation as well. So if we need to take decisions, instead of sending all the data to the cloud, we can actually localize our decision making. And once, let's say, the edge detects anomalies, then we can make some actuation decision without going back and forth. And also that would lead us to low latency on the system. Then in the case of scalability, because we can add multiple edge resources that are local to that network, it means that we can scale up the analytics. Privacy as well, like we saw, if you don't want to send all your data to the cloud for privacy and security concerns, then you can actually use the federated learning model to process your data locally and only send the model rather than the data to the cloud for aggregation. So the takeaways from this is basically that the IoT systems, we have different challenges like resource constraints, heterogeneity, and connectivity. And we are tackling that with learning and data reduction techniques. So some benefits, as we've seen, is that we can save data transmission costs, we can have quicker actuation, and make decisions faster. And we can also achieve privacy and scalability in the system. Okay, so let's see, do we have any question? Yeah, so please, if you have question, feel free, ask on the chat, and I'll answer with the little time we have left. And also feel free to connect with me on LinkedIn or on Twitter. That's my okay, Ella, how can we get started with putting data models on the cloud? So, what do you mean like machine learning models, I guess? Like, so we can actually, okay, machine learning models. So basically you can have, depending on your architecture. So you drop an architecture of what you, thank you, Mariana. So you can have depending on your architecture. So if you want to use the cloud computing approach where you're sending all your data to the cloud, so you can have a specific machine learning model that you deploy on the cloud. So even Google and some of Amazon and all that, they even have like machine learning platforms where you can do your machine learning training. They have like algorithms, sort of custom made algorithms, so you can check out those platforms for what they have, or you can build your own machine learning model and deploy it on the cloud. So they already have like structure in place to achieve that. I mean, the cloud platforms like Amazon and co. Okay. All right. Okay, you're working on cybersecurity and data privacy. All right. Okay. Yeah, sure. Yeah, please, let's connect, and thank you very much for joining. Yeah, thank you. Thanks. Thanks a lot. All right, so I'm signing up now. Yeah, Dennis, thank you for joining. Thanks, Sailaja. Thank you very much for joining. All right. Goodbye. Thanks, Sarah. Thank you, Judith. Thanks for joining. All right, bye.